Welcome to the HPC Best Practices webinar series, which is brought to you by the IDEAS Productivity Project funded by the Exascale Computing Project. This series is a collaboration involving the U.S. Department of Energy computing facilities at the Argonne, Oak Ridge, and the Lawrence Berkeley National Laboratories. I'm Osni Marquez from Lawrence Berkeley. Ashley Barker from Oak Ridge and I will be the hosts for today's webinar, Scalable Precision Tuning of Numerical Software. And the webinar will be presented by Cindy Rubio Gonzalez from the University of California, Davis. Cindy is an associate professor of computer science at Davis. Prior to joining UC Davis, she was a postdoc at UC Berkeley. She received her PhD in computer science from the University of Wisconsin-Madison in 2012. She's a 2020 BSSW fellow, as you can see in this slide, and the recipient of a DOE Early Career Award in 19, an SF Career Award in 18, Hellman Fellowship in 17, and UC Davis Campus Faculty Award in 14. Her work spans the areas of programming languages and software engineering, in particular on program analysis for automated bug finding and program optimization. She also holds a Bachelor of Music in Piano Performance from Autonomous University of Coahuila in Mexico, but I'm afraid Cindy will not have time to play for us today. So with that, Cindy, I'll stop my sharing.
Thank you. Thank you, Osni, for the introduction. Yes, let me share my slides. Okay. Can you see my slides now?
Yes.
Yes, okay. I'm gonna share my video. And let me just get this. Okay. I think we are good to go. Thank you again, Osni, for the introduction. I am very happy to be here today to present this webinar on precision tuning of numerical software. So floating point is a widely used representation of real numbers and is used in applications from many domains. Unfortunately, reasoning about floating point programs is often difficult given the large variety of numerical programs that can exist in these programs, and also the fact that most programmers are not experts in floating point. Because of this, a common practice found among programmers is to use the highest available precision, which often leads to poor performance. Luckily, tools have been developed to assist programmers in tuning the precision of their floating point programs. The purpose of these tools is to reduce precision while achieving a certain level of accuracy and/or improving performance. Today, I will introduce you to the problem of automated precision tuning. I will describe some of our research work in the area, and I will also discuss open challenges for scalable automated precision tuning of high-performance computing applications. Let's start with an example. So here is a fragment from a program that implements the Simpsons rule. The details are unimportant. Just note that there are two functions found in Simpsons. All floating point variables are declared in long double, which is an 80-bit representation. And there are two calls to math library functions, arccosine and sine. And these are on lines 2 and 3. So if we're able to tolerate some error in the result, then we may find a faster version of this program that uses less floating point precision. Now, here is such a program. The programs look identical in structure, but there are some important differences. The first is that 4 variables have been lowered from long double to double precision. Another 4 variables have been lowered to single precision. And furthermore, the call to sine has been replaced by a call to its single precision implementation sinf. So I would refer to this new assignment of types to variables as a type configuration. So it turns out that this type configuration leads to a program that runs 78.7% faster than the original program. Now, unfortunately, even for small programs like these, it is infeasible to find such a type configuration manually. So this is the motivation for the work that I will present today. So now, as shown in the previous example, the problem of precision tuning can be reduced to finding a type configuration that produces an accurate enough answer given while improving performance. So one of the challenges in finding such a type configuration is how to search efficiently over the types of variables. As you can imagine, the naive approach of exploring all possible type configurations quickly becomes infeasible as it is exponential in the number of variables in the program. Also, less precision does not necessarily lead to improving performance. For example, certain type configurations might incur in an excessive number of casting operations, which could result in worse performance. So we need a way to evaluate these type configurations to assess how profitable they are. This evaluation could be based on runtime measurements, memory usage, energy consumption, just to mention a few. Last, determining accuracy constraints is perhaps one of the most challenging aspects of precision tuning because it requires a deep understanding of the program under analysis. So this is about finding out how accurate the program needs to be and, in consequence, what error threshold to use during the tuning process. So several approaches for automated precision tuning have been proposed in the last few years. First of all, precision tuners may have one of two goals. Some of them focus solely on reducing precision while achieving a certain level of accuracy. However, such transformations are not required to lead to speed up. On the other hand, other tools consider both accuracy and performance, and this means that a speed up must be observed while achieving an accuracy goal. Second, there are two main approaches these tools follow. Static approaches do not require to run the program under analysis and may provide formal guarantees on the analyzed code. However, these techniques are often limited to straight-line code, and thus they may not be applicable to whole programs. On the other hand, we have dynamic approaches that outperform at runtime, and therefore they require program inputs to execute the programs. And in general, dynamic approaches are able to handle larger and more complex code at the cost of providing no guarantees for untested inputs. So far, we have been talking about variables and functions in our example, but for some tools, some tools might instead focus on instructions, so there are different granularities of the tuning process. And finally, there are also different granularities in terms of the level at which the tools work. So some tools work on the binary, some on intermediate representations, some other in the source code. So these choices may make an impact on the kinds of transformations that one can apply to the program, and also the effort that is involved in applying the recommendations that the tool provides to the programs themselves. So not mentioned in this slide is also the fact that tools might be focusing on specific programming languages or also on specific architectures. Now, in the rest of the talk, I will describe one of the earliest tools in automating precision tuning, which is called Precimonious. And I will also be talking about a more recent tool, HiFPTuner. So both of these tools implement dynamic approaches that consider both accuracy and performance when searching through variables and function calls, and these tools work on the IR level. So with this, maybe I can make a short stop to see if there are any questions so far. Otherwise, I will proceed to talk about Precimonious, our first tool.
No, you can continue.
Okay, great. So we have developed various techniques to tune the precision of floating point programs. So Precimonious is one of them. And Precimonious is short for parsimonious or frugal word precision. So this is a dynamic analysis floating point precision tuning. This is one of the earliest efforts in automated precision tuning. And as you see on the slide, Precimonious takes as input the program that you want to optimize. It will also require you to specify the error threshold that your program is willing to tolerate. So this is an input to the program. And also, it will need, because it is dynamic, it will need inputs to use during the tuning process. Now, if you can provide any inputs that are meaningful to your application, that's the best case scenario, but otherwise the tool will fall back on random floating point inputs. So now Precimonious performs a systematic search over the types of variables and functions in the program to determine how much precision they need. When the analysis will produce a listing of floating point variables and their suggested types. And when this configuration proposed by Precimonious is applied to the program, then the tune program will produce a result within the given error threshold for all the inputs used during the tuning process. And it will also be faster than the original program. So that's a general setup of Precimonious. Now, just to tell you a little bit of what Precimonious does behind the scene, I would like to touch into the search algorithm, which we said was a challenge in applying automated precision tuning to programs. So the search algorithm used by Precimonious is based on a well-known algorithm called delta debugging. So this algorithm is well known in the area of debugging. So what this algorithm does is that it simplifies and isolates failure-inducing inputs. And I have included on the slide a reference to the paper that introduces this technique for anyone who is interested in looking more into it. So during the search, Precimonious changes the types of variables and replaces function calls to evaluate their effect in both accuracy and performance, which together define the success criteria for a type configuration. So here, the delta debugging algorithm guarantees to find a local minimum, which is really good. So now, what does a local minimum mean? A local minimum means that if we change the final proposed configuration and lower the precision of any one variable, then the program will no longer satisfy the success criteria, which means that the program either will not be accurate with respect to the error threshold provided, or the program will not be faster than the original program. So let me graphically illustrate how the search algorithm works. So let's assume here that we have a program that has 8 floating point variables. So I am representing each of them by a circle, and here red denotes double precision, while blue represents single precision. So now, obviously, the first configuration to evaluate is to lower all the variables to single precision. And let's just assume here that this configuration does not satisfy the accuracy constraint. So we need to continue the search. Now, this algorithm is you can think of it as a binary search-like approach. And the first step is going to be to divide the set of variables into 2 equally sized subsets. In this case, each subset is going to have 4 variables. And then what the tool is going to do is lower these 4 variables in each set to single precision and test the program to see if it meets the accuracy and performance constraints. So let's assume, for the sake of the example, that these configurations are not good. They don't satisfy the success criteria. So we move on. So the granularity is further increased with each set consisting of only 2 variables. So each configuration is tested along with their complements, which are not shown on the slide. And assume here that only 2 of these configurations satisfy both accuracy and performance constraints. So one is picked, so we'll pick just the first one from left to right, and the search process is then repeated on the remaining 6 variables. So the process continues until no other configurations are found, and at that point, Precimonious is going to propose the last configuration that he found to be a good type configuration. Now, the algorithm is going to be exploring the search space and incorporate the feedback from testing each of those program variants. But one critical part in here is testing these program variants in the first place. So Precimonious is implemented using LLVM, and it automatically transforms the LLVM intermediate representation of the program so that the type changes are equivalent to modifying the program at the source level. Now, working with the LLVM IR gives us some flexibility on the kinds of transformations that Precimonious can apply, although the ones that I'm discussing today are limited to variable types and replacing function calls. So recently we developed a clamp plugin that can also be used instead to automatically transform the code at the source level, which facilitates transferring, these recommendations to the application itself. Now, the end goal is to run the transform program to evaluate that a given type configuration is good in terms of accuracy and performance. So Precimonious is open source, and its most recent version can be found at the first URL on this slide. Precimonious was part of a supercomputing tutorial on floating point analysis tools that was organized by Ignacio Laguna from Livermore last year. So I am also including on the slide the link to the website for the tutorial, where you can also find materials for other tools in addition to Precimonious. So this is fpanalysistools.org. And the last URL also has tutorial materials along with a Docker file to facilitate installation of Precimonious in case you are interested to try it. In terms of how to use Precimonious, so the current implementation of Precimonious works for C and C++ programs. So it has been mainly tested on C. And we are in the process of developing a similar precision tuner for Fortran code, which I am really excited about. If you want to use Precimonious, the first requirement will be that you will need to compile your program using Clang. So you need to be able to compile your program using Clang. And that is because, as I said, Precimonious works on the LLVM bit code of the program, which is generated by this compiler. Second, you will need to know where the final result is computed in your program, because Precimonious will require you to add a few annotations that will check the accuracy of the result, and it will also keep track of the performance of the transform program during testing. So the tutorial includes some concrete examples that you could use as a model. So we provide some utilities functions for this. Third, you will need to provide an error threshold when adding the annotations. So this error threshold is used to determine whether a result is accurate with respect to the original program. So here are various examples of error thresholds. So you can provide any error threshold that your application should obey. But I also included some examples here. So for instance, 10 to the -4 roughly means that the result after tuning requires 4 digits of accuracy with respect to the original program. Optionally, and for better results, you can provide inputs to use during the tuning process. Otherwise, as I said before, random floating point numbers will be used. And if applicable, you can also specify if any functions or variables need to be excluded from the search space, or you want to focus on. So either excluding or including. So in the end, Precimonious will provide the proposed types for each variable considered throughout the search and any recommended function call replacements. And this type configuration is meant for to assist you in tuning your program. So in my view, this should be served as a good start for you to identify code areas in your code. Code areas that could benefit from tuning. So now some limitations. So Precimonious, as other dynamic precision tuners, produce type configurations that rely on the program inputs tested. So there are no guarantees if a worst condition input is given. So my first recommendation, if you want to use a dynamic tuner like Precimonious, is to provide inputs that you know cover important corner cases for your application. So furthermore, it's good to be aware that the research community is also actively working on developing automated techniques for generating floating point inputs that maximize error. So those tools could be good candidates to provide meaningful inputs for your application to consider doing tuning. So it's kind of solving two problems, helping you test your application and also making sure that the precision tuning is more robust. Now, scalability limitations are likely if you have a long-running application, as Precimonious needs to run the code multiple times during the tuning process. So of course, we always need ways to reduce the search space and the number of runs required by the analysis. So a quick tweak here, if you have a long-running application, is that you could focus on a specific area of your program as opposed to the full application. So Precimonious gives you the flexibility to provide this information. And in my experience, synthesizing smaller but representative workloads can also make it feasible to run such an analysis on a large application. And these are some of the ways we are addressing these kind of problems right now when trying large applications. So finally, although the configurations found by Precimonious, I just gave you an example today, which was a Simpsons program, but in general, the speedups are decent speedups. There is definitely room for improvement. So in particular, Precimonious is a black box approach that does not exploit the relationship among variables. So here, a natural question is, can we do better? Can we leverage the program to find configurations that lead to higher speed up? So in the remaining of the talk, I will describe HiFPTuner, which considers the relationship among variables to reduce the search space and the number of runs needed during the tuning process. So those are like the two things that HiFPTuner addresses. But before I go there, I would like to stop again to see if there are any questions so far that I could address.
Yes, Cindy, there is one question. Is there a possibility of using these tools with TensorFlow or PyTorch?
So the current implementation is only for C. So let's see. So we're talking about Python. I would need to look more into it. So I haven't applied, to like machine learning applications or anything like that. But I would be really interested in discussing more about that. Yeah. And I'm not aware of any related work that is doing that. So I'm going to be providing some usable resources later on for other tools that are doing this kind of work. But I am not aware of anything dealing with those kinds of libraries. Yeah.
And there is another question just came in here. How expensive is to run the tool?
Yes, so it will depend on two things. So one is the number of variables that you are considering in your search space. And the second one is how long it takes to run your application, because we need to be doing testing every time. So for, mid-sized programs, it might take like about an hour, it really depends on how large the search space is and the running time of the program.
Another one here, Cindy. Mm-hmm. Will the Fortran support you talked about rely on FLang?
No, it will not. Yes, we are not. Yeah, we are moving from the LLVM art to do source-to-source transformation, so we will not be dependent on FLang.
Okay, please go on.
Yes, sure. So more recently, we developed HiFPTuner. So this is short for Hierarchical Floating Point Precision Tuner. And HiFPTuner, in contrast to Precimonious, HiFPTuner is a white box approach and that leverages the relationships among variables to reduce the size of the search space and the number of program rounds required during the search. So Precimonious follows a black box approach, grouping variables arbitrarily. So this means that variables used in the same expression may be assigned different floating point types. Now, treating variables independently leads to a larger search space and therefore to a slower search. Furthermore, an excessive number of typecasts may be introduced, which often results in less or no speedup. So looking at this from another perspective, we plot the precision in number of bits used by each instruction during the execution of the small Simpsons program that I presented at the beginning of this webinar. So on the left, we have the plot for one version of the Simpsons program, which is unoptimized. And the local minimum found by Precimonious is located in the middle of the slide. So this program executes some instructions in single precision, but it also makes more shifts in precision than the original program. Now, on the other hand, the global minimum, which is like the best configuration we found through exhaustive search, executes fewer instructions in single precision, but it also makes fewer shifts at running time. And this results in a larger speed up of 90%. So now this suggests that a more uniform precision assignment based on the usage of variables could reduce precision shifting and thus further improve performance. Now in this work, we leverage the program to perform such informed precision tuning. And our three main insights are as follows. So first, related variables can be pre-grouped into a hierarchy based on their usage and assigned the same type. Second, the search is then performed on these groups rather than on individual variables, reducing the search space. And last, because variables in a group are assigned the same type, the number of typecasts is reduced, leading to larger program speedups. So following the previous example, here we have the 8 individual variables, which in HiFPTuner will constitute the level 0 of the hierarchy. So communities of variables are then going to be detected based on variable usage, and these communities will form the new top level 1. And this process is going to repeat iteratively until no new communities are found. Now, once we have this community structure of variables, we will start the hierarchical search, and the search will start at the top level of the hierarchy. So in this example, the search will start with only 2 elements in the search space, these 2 communities of variables. So assigning a type to a community means assigning that type to all the elements in the community. Now, the resulting configuration will then be passed as initial configuration to the next level, so level 1, going down. And this will effectively prune the search space, and it will allow us to refine the type assignment if needed as the communities break down. So just to tell you a little bit more about what is happening behind the scenes, here I will start with the requirements, which are similar to Precimonious. So you will need to provide the source code that you want to tune and some inputs to use during the tuning process and an error threshold. And given this information, we are going to perform a type dependence analysis and edge profiling to construct a weighted dependence graph. So second, we formulate the problem of grouping variables as a community detection problem in networks. And we use an existing popular algorithm known as modularity maximization algorithm to solve this problem. And I'm referring here to some related papers. So we apply community detection iteratively on the weighted dependence graph to construct the community structure of variables. So finally, we apply our hierarchical search algorithm to tune the program using this community structure of variables. And as a result, we're going to have a recommended type configuration that both speeds up the program by reducing precision with respect to the accuracy constraint provided. Now, also going back to the example that we saw earlier, I'm not going to go in detail here, but I just wanted to give you a high-level idea of how this looks like. So here we have the weighted dependence graph for Simpsons. So here, each node is a variable in the program. Edges mean relationships or that variables are used in the same expressions. And here the numbers are basically the weights, which represent how often that relationship is used at runtime or is executed, and that is captured by profiling during the construction of this graph. Now on the right, I have the ordered community structure that we get after applying the networks algorithm. And here you can see that this has two levels, this hierarchy. At the top level, we have only 3 communities, and you see like what variables are in each community. And the good news here is that HiFPTuner, leveraging this community structure of algorithms, was able to find the type configuration that we found through exhaustive search, while exploring fewer configurations, which were 24, and this was basically 5 times fewer configurations than Precimonious. So in general, in our experiments running both tools on a small set of programs, we found that the search space at the top level of the hierarchy was reduced by 53% on average in comparison to Precimonious. We also found that HiFPTuner performed a faster search for 75% of the programs, exploring 45% fewer configurations. And finally, HiFPTuner found better configurations for half of the programs, while for the other half, it was able to find configurations comparable to those found by Precimonious. However, it was able to find them faster. So HiFPTuner is open source, and it was also part of the supercomputing tutorial, the supercomputing tutorial of floating point analysis tools that I mentioned earlier. And you can find the code, examples, and a Docker file in the URL on the slide. And in terms of requirements to run HiFPTuner, those are the same as Precimonious. So HiFPTuner also uses LLVM IR. So you will need to compile your program using Clang and provide inputs, provide the error threshold, and so on. So it's the same setting as Precimonious. So as a way to summarize what I have presented so far, here's a tool comparison including another of our tools that I did not present today, blame analysis. And Precimonious considers both accuracy and performance and works for what I would call medium-sized programs, but it requires a run for each type configuration. And the order of the variables may affect the results. So here, as someone from the audience was asking, so the runtime of the search will really depend on how large the search space is for your program and how long it takes to run. Yeah. Now, HiFPTuner groups variables based on their usage, resulting in a more efficient search and better configurations. However, it requires profiling and it still requires a run for each explored configuration. And finally, blame analysis, which is a tool I did not describe today, is a tool that performs shadow execution to identify variables that can be allocated in single precision. So in contrast with Precimonious and HiFPTuner, blame analysis requires only one single run of the program, which is good. However, in that one single run, a lot of work is being done by the shadow execution engine. So there is an overhead in this one run, which we found it to be about 50x on average. And also because blame analysis is doing one single run, it is not taking performance into account. So the configuration that blame analysis might give you may not lead to program performance improvement. So one thing that we did find is that by combining blame analysis with a performance-driven tool like Precimonious or HiFPTuner, we can find a type configuration that does lead to a speed up while also reducing the search space. And here is a reference to the paper that describes blame analysis in case you are interested in learning more details. So now, what are the current challenges in applying these techniques to HPC applications? So the first big challenge for any dynamic precision tuner is the one that I mentioned, towards the beginning of the talk, which is that all the type configurations produced by these tools are going to rely on the program inputs tested during the tuning process. So some open questions in this regard are, can we easily characterize the applications for which this is problematic or this is not a problem so that we can know what applications are a good fit for this kind of tools? The second would be, can we leverage application-dependent correctness metrics to have more confidence on the results? So metrics that probably do not, are not based on running the application at one particular point. So another research direction is to combine the strength of static-based tuners and dynamic tuners. And this would be to leverage scalability. So maybe some parts can be done statically, some parts of the analysis, and also infer some information so that we don't have to run these tools that many times. And there is some work in this area. And in general, one area that I explored many years ago was using cost models to evaluate the impact of this type configurations on performance. So if we could do that statically, then we could perhaps not have the need to run to run every configuration to evaluate them. And that would be a huge saving for the tools. So as we try our tools on more real-world applications, there will always be new scalability bottlenecks. And we need to further reduce the search space and the number of runs, which is related to the point I just discussed. And yeah, so I guess what I was meaning to say in this part was like the stuff about the cost models. I think that could make a huge impact on the applicability of these tools. Now, also the configurations in general lead to decent speed ups. We do not know how far we are from the best configurations. So for the Simpsons program, we were able to do an exhaustive search to compare, but that will not work for most programs. Otherwise, we could just do the exhaustive search. So how can we get a sense of how far we are from the best configuration? Are there any other program transformations that we could explore besides changing variable types and, and replacing function calls? Can we incorporate any domain knowledge to guide the search to find better configurations? All those are open questions. And finally, in my experience, it is still difficult to find programs to test precision tuners at scale. So I really believe that we need to reaffirm and establish new collaborations among application and tool developers. And this is going to be the key to push the boundaries of automated precision tuning. So please don't hesitate to contact me if you are interested in being involved in such an effort. So here are a few useful resources if you are interested in learning more about automated precision tuning. Unfortunately, I didn't have much time to talk about static analysis techniques or hybrid techniques. So here is a non-exhaustive list of very recent papers on the topic. And I also wanted to point out a recent survey on reduced precision computation that I encourage you to look at if you would like to learn more about like the different categories of tools and their pros and the cons. So I also wanted to mention this website from FP Bench that does maintain an exhaustive list of community tools. So there you will not only be able to find links to the papers that describe the tools, but also links to the tools themselves. So that's very helpful. And finally, I also wanted to point out a webinar that Ignacio Laguna gave last year on floating point tools, also here, that you might want to take a look. So before concluding, I wanted to briefly mention this supercomputing workshop that I am co-organizing since 2017. This is a workshop on software correctness for HPC applications. So this is a workshop that has been like one channel to start building up this community of tool developers and application developers, and it's a great place. So unfortunately this year, the workshop is going to be virtual as a whole conference, but if you are planning to register for supercomputing and you have, 4 hours available to attend this workshop, I would really encourage you to do so. So to summarize, precision tuning can have an important impact on the performance of programs. There has been great attraction in the past few years, so with many different approaches being proposed. Today, I discussed 2 of the tools we have worked on. So Precimonious, which is one of the very first on automating the precision tuning, and HiFPTuner, which is more recent, and you saw, yeah. It leverages more the program to reduce the search space and find better configurations. So a lot of progress has been made, but there are still challenges and opportunities to apply precision tuning at scale. And I strongly believe that the key lies in a strong collaboration among application and tool developers to push these tools to the next level. So with this, I would like to conclude the talk by thanking my collaborators from UC Berkeley, Lawrence Berkeley National Lab, Oracle, and UC Davis. So these are collaborators on the work I presented today. And also thanks to the agencies currently sponsoring this research. So with this, I am ready to take any remaining questions.
All right, Cindy, thank you. Yes, we do have questions here. Let's see where to start here. There is one in the chat, actually two. So do these tools support precision tuning on GPUs or mixed CPU-GPU systems?
Yeah, that's a great question. So the current implementation of Precimonious and HiFPTuner are solely focused on CPU. However, in the resources that I just showed you, there are a couple of papers that have recently applied these techniques to GPUs. So yes, the techniques have been adapted, but it's not these specific implementations, but I can point you out. So one of them would be, if I go back here, well, the very first reference here, like GPU mixer, is one example of a technique that has adapted the Precimonious, approach to GPUs. Mm-hmm.
An interesting one here. Would the tool support templated types like in C++?
So the applications we have applied these tools to do not have those. So I would need to, we will need to try a few examples to make sure that the transformations are supported. I wouldn't be surprised if they are not right now. But yeah, this is one of the cases in which, talking more offline to see a specific concrete examples would be very helpful.
Okay, Cindy. What are the advantages and challenges of working on the source code compared to the LLVM IR, apart from removing the dependency on a specific toolchain?
Yes, so in my view, and the reason why we originally chose to work at the IR level was that I believe that working at the IR level gives us more flexibility to apply program transformations. So maybe for changing types and replacing function calls, the advantages don't come as easily. But imagine, maybe modifying loops or splitting loops or doing other kinds of transformations will be a lot helpful. Like it will be easier to apply at the IR level. Yes. And that's one of the motivations that we were like trying to look, more into the future, into potential additional transformations. But one thing that I would like to say is that also working at the IR level might bring difficulties in terms of mapping these results to the source code, right? Unless you have an automated way to do it.
All right, and then I think the next question is related to the previous somehow. So if we have a C++ or C code to run on some exotic hardware like the Cerebras CS1, could we intercept the IR and apply these tools? How do we give the optimizer the numeric output and timings?
So yes, okay, not exactly yes, but so as long as you are able to produce LLVM code for your code in this, in this architecture, we should be able to apply the analysis. So that's my understanding. So yeah, at least for the implementations that I described today. Yeah. So one requirement here is that you are able to get the bitcode file for your code.
All right.
Let me know if that didn't answer the question. Yeah.
Okay, so the participant is, of course, could type, I'll say a little more.
Mm-hmm.
Is there a way to only apply these technologies to part of the code? For example, for a preconditioner, right? I would be willing to give up precision, but I don't want to reduce accuracy for the nonlinear solve. I might have missed that in the talk, or would I just create a code that just calls the preconditioner by itself?
Yes, that's a really good question. So yes, it's possible. So in particular, the Precimonious implementation allows you to specify if there are certain variables or functions that you do not want to include in the search space. And then, the types will not be taught for those. And similarly, if there is a particular area that you want to focus, depending on what is bigger, right? So if you want to omit everything for one function, there is a way to specify that. If there is one function that one function of functions that you do not want to modify, there is also a way to specify. So yes, you can narrow down what part of your code you want to focus on.
I don't see any further questions here. We can always wait a little.
Yes,
a
so
minute.
yeah, so I just wanted to reiterate that I am really interested in connecting, and in helping also to run these tools. You know, the only, in my experience, the only way to find, like, you know, interesting ways to improve these tools and make them more usable is to have these examples that expose the problems. And yeah, and I'm hoping that many people in the audience, you know, have access to these applications. They're curious to know whether we could do precision tuning on them. So please reach out if you have, you know, such an application.
Okay, Cindy, thank you very much. I'd like to thank everybody that joined us today for also as well. So we want to improve this series. So please give us feedback. There is this survey. These slides are already available actually in this Scalable Precision Tuning, exascaleproject.org/event. So the recording will be available very soon, and the same, Cindy will go through the Q&A and answer the questions there. I'm just repeating what she said, so if you have further questions, feel free to contact her. Right, Cindy?
Yes, please.
And so then I'd like to announce the next webinar in the series. It's going to be on November 4th, Reducing Technical Debt with Reproducible Containers. And the webinar will be presented by Tanu Malik from the DePaul University, and folks can already register for that, sign up for that webinar. So again, so thank you all for joining. Thank you, Cindy.
Thank you.
And that's it. See you next month. Bye-bye.
Thank you, everyone.